Log on, tune in, find out. Another good idea from Cambridge.
Pleasure to introduce Tony Joseph from the Weizmann Institute, who will tell us about an algebraic slice in the coadjoint action of the Borel.
Okay, first of all, I'd like to say I tremendously enjoyed myself in Cambridge. Not only is the Newton Institute a wonderful place to be, but Cambridge itself is very nice, with more restaurants than I remember in Oxford, and it only makes one wonder if the colleges are feeding their members properly. So the subject of my lecture is based on three wonderful theorems in the invariant theory of simple Lie algebras and their possible generalization to non-reductive Lie algebras. So let me just remind you what these theorems are. So theorem A, which is due to Chevalley, and is the following. We take G a simple Lie algebra. Then we can form S of G, which I'll use as a general symbol for the symmetric algebra over G. And we may also take the G invariants, which I will generally use a capital G for the group. We view those as the invariant polynomial functions on the dual. And I'll use for this the letter Y of G. And his theorem is that this is a polynomial algebra. The second theorem is due to Constant. And let me just say before I come to it that the proof of this theorem uses some quite remarkable results, namely the Weil character formula and that the Weil group is generated by reflections. Now those are very special things which concern only the semi-simple case. Now let me define n of y of let me define this set n, which will eventually sit inside G star, as the zero variety of the augmentation. In other words, the elements in G star which vanish on homogeneous polynomials of positive degree. Sometimes I'll just refer to this as the nil fiber. And let's choose y to be a regular element in there. Now remember that we have a coadjoint action of G on G star, and a regular element is one whose orbit is of maximal dimension. And when I write this, we already are relying on a not entirely trivial fact that this set is non-empty. And let V be a complement to add G of Y living inside G star. And then theorem B, which is due to Constant, is that if we can improve this theorem by saying that when I take Y of G and restrict it to this set Y plus V, then and we take the, so we restrict the elements of here to here, we get we go from this polynomial algebra to this algebra functions on this affine set. This map is an embedding that's fairly easy, but actually Costant observes that it's an isomorphism. And what it means is that by this trick of translating by y, we have linearized the elements of y of g. That's sort of rather striking, and one might not immediately see it from that simple formula. Now, this theorem also uses some fairly special results for the semi-simple case. It uses the Jacobson-Morozov theorem, which manages to embed y in a triple, usually known as an S-triple, of elements which form an SL2 subalgebra. And not only is y regular, but all three elements, x, h, and y, viewed as elements of G star through the killing form, all of these are regular, and this is called a principal S-triple. And what you should note is remarkable about this is that add h on y, which I'll take to be minus y. Some people put a 2 there, but I'll just take it to be minus y. This element is an eigenvector on the one hand, so it's an eigenvector, and on the other hand it's regular. And these are sort of almost contradictory properties. And so it's not quite so trivial that this is possible. Now, for the next theorem, which is theorem C, which is probably claimed by quite a few people, I'll put down 3 initials, Mishenko, Fomenko, I just don't want to write out all these long names, and Tarasov. And they did the following. They took an appropriate, well, let's see how I want to present this. First of all, with this element h, we can take the dual, or G itself, it doesn't really make any difference, and grade it by the H eigenvectors, add H eigenvectors. So this is the add H eigenspaces. And then we can introduce the positive eigenspace, which you... well, this is the principal S-triple. Yeah, but this is the principal S-triple. I just don't want irrelevant 2's. I'm very economic. This is theory of economics. So, then we take this thing, which you may recognize as a Borel. Of course, I can identify G with G star, so you might recognize that as a Borel. And then I take a suitable H star in G star inside the 0 eigenspace for add H, and also regular. Now that's also not obvious that it exists, but of course, since you can identify G with G star, you can just take H star to be H, and then you can just think of the following set, which is, well, actually algebra, which is defined by shift of argument, simply as differentiating with respect to H. So we introduce this shift of argument algebra. And the reason why this subject is so sexy is because it has applications to mechanics, and in particular Toda lattice theory. And the result of these fellows put together, I might say, these people on the one hand and this person in addition, is that if we take this bigger algebra, which is got by differentiating, then it maps isomorphically by restriction of functions to C of y plus g star greater than star there, just to be consistent, greater than 0. This actually, this formulation of the theorem has some interesting consequences. For example, it implies not only that this is a rather big algebra, but it's equal to its commutator with respect to the Poisson bracket. So this is actually Poisson commutative and maximal in the sense that it's equal to its Poisson commutant. So as I said, these three theorems rely on lots of data results from the semi-simple case, and it seemed almost inconceivable that you could have any generalizations to wide classes of other Lie algebras. But however, that's changed a little bit, and now quite a few people are working on this. I'm going to mainly talk about my own work, which is extending these theorems to the biparabolic case. Now, what does that mean? If you forget about bi, that's everybody knows what a parabolic subalgebra is.
I don't understand what does it mean, why H star G?
I didn't really want to go into all the definitions, but it just means that it effectively means you take the polynomials here and differentiate them with respect to H.
So you take
So-
the invariance and you differentiate
Yes.
the direction of it.
Yes, that's right. So if the invariant was this, then you would take H.
Okay, and
So you got the polynomial
and you
in.
keep the invariance as well. So you apply all the differentials you can.
Yes, yes. Yeah. And of course the So let's fix a triangular decomposition of G. Which effectively means picking a set of simple roots. Well, it means making various choices, but in particular specifies a set of simple roots. And let's, if we have pi 1 in pi be a subset, then of course associated to this there is a standard parabolic subalgebra. And if we take pi 2 to be another subset, then we can form the opposite parabolic subalgebra, and then we can form what I call a biparabolic subalgebra, which is p pi 1 intersection p minus pi 2. Surprisingly, these have hardly ever appeared in the literature. If you consider the number of times parabolics appear and the number of times biparabolics appear, it's almost 1 to infinity. It seems like these were first introduced by Elashvili, and later work of Kirillov carried this further. Kirillov called them seaweed algebras because if you sort of look at the way that they sit inside SLN, they look like a piece of seaweed. I don't have time to draw it, but it's fun. Okay, so, but in any case, for me, it turns out that all the proofs fit nicely into this situation. So it's better to talk about biparabolics and parabolics, although that's not really essential. So the question you can now ask is, can we say something interesting about the invariance in the symmetric algebra of this biparabolic? It's of course an algebraic subalgebra. So one can expect that to be at least fairly well behaved. Now, and I shall only talk about the case where this is not G, not the original Lie algebra. In this case, this object is reduced to scalars, so it's not very interesting. So rather than this, one considers the semi-invariant subalgebra, which just means that I don't look at invariants, but the sums of semi-invariants. So this is a direct sum over the set of lambdas, which will be in some set capital lambda, which in fact is sitting in pi 1 intersection pi 2 orthogonal. So it dies on pi 1 intersection pi 2 of certain weight spaces. And I'll use this symbol to mean that this set is non-zero. So in fact, this will be, in general, a proper subset. And then there's a trick of independently discovered by Borel and Chevrolet, who observed that you can go back to this situation if you replace q of pi 1, pi 2 by its truncation, which is a fairly trivial thing. I'm not going to talk too much about this. It's just the kernel of the lambdas as lambda runs through this set lambda of weights. I'm sorry, this is the kernel of the lambda as lambda runs through the weights. And all that's happening is that you've taken your Cartan subalgebra here and similarly truncated it. So the only difference between this guy and this guy is that it has this smaller Cartan subalgebra. Okay, in that case, we find, and this is the point of this construction, we find that we have an equality between these two objects. So we've got back to the invariant situation. So the invariants in this truncated algebra are the semi-invariants in the full biparabolic. And now, analogous to...
Invariance means invariance with respect to a joint action?
Yes. Oh, well, yeah, okay. So that means you think of this as invariant polynomials on Q star.
Invariant under big Q.
Under big Q, yes. So these are polynomial functions on Q star, and you're looking at the invariant polynomials. Okay, so analogous to these previous theorems, we have the following. Theorem 1 is that y of q of pi 1, pi 2 is polynomial in most cases. Now, I'll define what that means later, but it means all in types A and C in particular. And the proof involves certain upper and lower bounds on this, the size of this algebra, and the upper and lower bounds don't quite coincide because of certain strange factors of 1/2. So there are strange 1/2 factors which ruin the coincidence of upper and lower bounds. And this is one of the things that I want to discuss, these 1/2 factors. So theorem 2.
So you actually have examples when it is not polynomial.
Well, yeah, there's an example of Yakimova, which which is done by a computer, which you just have to believe, in type E8, when the parabolic is what I call the Heisenberg parabolic, and she managed to disprove two conjectures with one theorem, because she showed that if G is of type E8 and x beta is the highest weight vector, then G upper x is a truncated biparabolic, but it's also, as it's written, the guys which commute with x of beta, and this guy is not polynomial. It's most distressing, but that's what we have. So theorem 2 is that this theorem B extends for suitable choices of y and v. So in theorem B, we had some choices of y and v, which didn't have to be specified terribly precisely. We just took a regular element in this nil fiber and a complement to this. Here they have to be specified much more carefully, and this is only true for G, the original Lie algebra and everything in which everything is embedded, of type A. And the third theorem, which is even more restrictive, is that theorem C extends to Q pi 1 pi 2 in type A if the index, which is the codimension of a maximal orbit, coadjoint orbit, is the rank of the Lie algebra, rank of the original Lie algebra. Well, this is all very nice, but we have some rather distressing conditions here, which means that you must throw away certain simple Lie algebras. And this is something which upsets people. They say, well, if you're going to prove a theorem about semi-simple Lie algebras, it should work for all cases. So the goal now is to try to reformulate some of these results, some of these theorems, if you like, so that you can, so that they become true for all cases, and that they don't look terribly much different to what you originally wanted to prove. Whether or not this is good for anything, I don't know, but that's what we want to do. So let's go and take the example as an example. So we want to reformulate, in particular, theorem A, theorem B rather, so that it works more generally, and particularly I will take specifically when the biparabolic, or the truncated biparabolic, Q, is simply a truncated Borel, which just means I'm taking pi 1 to be pi and pi 2 to be the empty set. Now in this case, it's known, and in fact by extending some results of Constant, unpublished results actually of Constant, I'd already proved in 1977 that this algebra, when you take pi 1 to be pi and pi 2 to be the empty set, is polynomial. So at least for this case, theorem A holds, or theorem 1 holds. But on the other hand, theorem 2 doesn't hold. It breaks down badly outside type A.
Sorry, Tony, could you tell what is BE?
It's B.
It's just B.
B is the Borel.
What's
And E is this truncation which is needed to get rid of semi-invariance. It just makes the cartan a little smaller. So if you like, if you don't want to think about B of E, you can think about the semi-invariant algebra of B. Theorem 1 holds, but theorem 2 breaks down already for B2, for SP4. That's pretty drastic. Okay, now let me explain rather precisely what is the trick that is going to turn a false theorem into a true theorem. And let me be totally unsophisticated and write this in a way which may make you feel that it's a rather dirty trick. But it's not entirely trivial, nevertheless. So what we're doing is we look in particular for y in the dual of B such that, well, this is one of the properties it has to have, and this is going to be, if you like, the point in the nil fiber, such that B, well, not, maybe I used another letter, A of y is non-zero for all weight vectors in y of B of E. Okay, so this is one of the things you would like to do if you were to get theorem 2 to work. And the modification we're going to make is that we're going to give ourselves an alternative. So let kappa be the Chevalley involution. And of course, kappa of A is sitting in the opposed algebra. And now we're going to weaken our demands. Instead of this, we either have either this or this. But either one or the other, if in addition, so these two conditions should hold, if A is a generator of the polynomial algebra. So this will give us some additional flexibility. I can't say it means very much, but the proofs work rather nicely and involve lots of remarkable coincidences. So before I can get to that, let me just describe more precisely the nature of this polynomial algebra. So
Sorry, I don't understand. Because you say that K of A is an element in this V algebra, then it's also a generator of...
this is a Chevrolet element. Yeah.
Ah, because these are functions on the dual, so okay, I understand.
Yeah, you might say
why
this
is
is
it
a crazy thing to do.
But
Okay.
why is it invariant, you say? Why? Ah, okay.
Okay, that's grosso modo what we're going to do. And so let me describe more precisely, or description. I haven't given any description, so description of y of v of e. So, so jumped ahead a bit. So, so this is a module for the Cartan subalgebra. So it has weights. So let lambda be the set of weights of y of BE, or if you like, S of y of B, with respect to the Cartan. Then, as you might hope, if this is going to be a polynomial algebra, then lambda is a free semigroup. Generated by some set lambda 0. And lambda 0 is given by the following very simple recipe. Lambda 0 is the set of all elements of the form P alpha. This is the French P that has been foisted upon us by Bourbaki, minus W0, which is the longest element in the Weil group, as pi runs through the set of roots. And then there's a mysterious factor, epsilon alpha, which can be either 1/2 or 1. Depending on alpha, of course. Sometimes it's 1, sometimes it's 1/2. And this is, if you like, the troublemaker in the whole theory. In types A and C, epsilon alpha is always 1. Now, if you want an example of one of the more troublesome Lie algebras, you can take E8. This is a presentation of the root diagram of E8. And the places where you have 1/2, the simple roots for where you have 1/2 are just here. And they alternate along the diagram. Now, if you like, this is just a curiosity, this 1/2. It's also a big nuisance. But now, in what I want to present, this 1/2 will be absolutely essential to get an isomorphism, to get the surjection. Otherwise, I would have ended up with quadratic polynomials. So it's rather satisfying that this irritation is actually exactly what we need to get the theorem. And it's one of the coincidences which occurs in this theory. Now, you may, of course, notice that it could happen. So of course, minus W0 acts on pi, and it can happen that it has non-trivial orbits. And in that case, the dimension of this semi-invariance of, in that case, epsilon alpha is always 1, so I can just forget about it. And this has dimension 2, or its dimension is equal to the cardinality of the orbit. Maybe I'll just say it like this: 2 if pi alpha is not equal to minus W0 pi alpha, and 1 otherwise. So if you like, the number of generators of S of y of b is going to be 2 whenever the weights coincide, but is 1 otherwise, which means that the total number of generators is exactly the rank. So it means that the number of generators equals the rank of G. Now, on the other hand, if I look at the part which comes from the nil radical of B, so S of y of B contains the invariance in n plus. Contains it. And it differs from it by exactly not having the additional generator which occurs when you have this situation. So, in fact, y of n plus has the property that the dimension of y of n plus at any weight, but in particular the generating weights, is always 1, of course, if mu is in the set of weights. So now, and this is partly the motivation for making this strange operation of converting the theorem that I had before into a true theorem. Part of the motivation comes from the following. If this is true, then you can make the following map, a linear map, from S of y of b to y of g. So from the invariance of the Borel to the invariance of g. The referee of the paper actually said to do such a thing looks like a joke. I don't know if it's a joke, but it was fun anyway. And this goes in the following way. You take your, first of all you do this, you construct this map on each weight space. And of course, if you have a weight space, if you have a vector of weight mu here, then you can multiply it by the corresponding vector of weight minus mu, which is unique up to scalars, in the algebra where n plus is replaced by n minus. Then you can recognize that this is a highest weight vector, this is a lowest weight vector, and apply to this and u of g to get a module. And of course, that's just the tensor product, or the image of the tensor product, generated by these highest and lowest weight vectors. So it has exactly one copy of the trivial module, which of course may disappear when you take this image of the tensor product living inside S of g. So the dimension of the g invariance here is at most 1. Now, so how to get the map? So let me define the map to be C of B mu, defined on this part only, is going to be simply the element Z of mu lying in here, so z of mu will lie in here. And to ensure that I have a linear map, I will pick such that A minus mu B mu minus Z mu will be killed by the augmentation. I'm not quite sure that's what I want. No, sorry, that's not what I want. This will be sitting inside add u of g augmentation applied to A mu B mu. So if A minus mu is fixed, and you make this operation, you take that particular Z mu, so that the difference is in the augmentation here, you get a linear map from this piece to here, and then you just extend it. So we now have a linear map from here to here. And the theorem, if you like, it's not a great theorem, but one has the following, that phi is a linear isomorphism in types A and C, is not injective otherwise, but conjecturally, but I would conjecture if you like, conjecturally it is surjective. There's reasonable reasons for thinking it might be surjective. And there's actually a version of this map at the level of u of g, where you do almost the same thing, but you omit all these epsilons, where you could hope that the map's even bijective, but that's another issue. Okay, so what it means is that I would like to believe that this algebra, which is formed in this way, A of g, which is the direct sum over mu in y of n minus at weight minus mu, together with s of y of b at weight mu, has the property that if I take add u of g on A of g, and then take the g invariance here, then this equals, and there's the question, this is equivalent to surjectivity, is y of g. So in order to study this problem, one might want to understand A of g a little better. And the principle, although not what really quite happens, is that we have the following theorem. The theorem B prime, if you like, the way I've modified the theorem B from being a false theorem into a true theorem, is that there exists a good choice of y in n regular and v in G star, such that the restriction map from this algebra A of G, which is a polynomial algebra, becomes an isomorphism onto y plus v. In actual fact, that isn't entirely what I prove. Some very slight modification of it, but it's what's proved in the case where -1 is in the Weil group, and I won't detain you with the exact statement. Except in E6, by changing things in a rather unnatural way, I can get this to work in all cases except E6, and maybe it will work in E6 too. But in fact, what I do is I make a very slight modification of this by sort of shunting these extra invariants from here to here. Doesn't change the whole principle of why I want to look at A of G in the first place, but that's what we do. Okay, so as I explained, the idea is to give ourselves some extra flexibility. I think I've rubbed it out. Yes, unfortunately, I've rubbed it out. The extra flexibility in choosing a y which may vanish, for which vectors here are non-zero on the y, or they're non-zero here. So that's the extra flexibility that we have. Now, basically we have this theorem in which y has to be an element in this set n regular. And unlike the constant theorem, we have to be extremely careful about its choice. Now, you may think that's good, or you may think it's bad. So you have this rather nice theorem of constant, which is sort of rather easy to prove, but it works for any y. Here I have a theorem which is difficult to prove and only works for a very special y. And some people might think that a virtue, and some people might think it a fault. I don't know, it's up to you. But in any case, that's the situation. So how do we make this very special choice of y? So let me just explain again the idea of what's going on. So now what we're trying to say is the following. If I call this thing delta alpha, then we want y, we need y to satisfy, this is what I said before, but just let me remind you, either y of n plus of delta alpha on y's, this is one-dimensional, remember, is non-zero, or y of n minus at weight minus delta alpha of y is non-zero. Before, we would have demanded that only one of them is true. Doesn't really matter which, but all the time. And now we're giving ourselves the extra flexibility that we will be sort of broad-minded. Either this guy is non-zero or this guy is non-zero. Now, what is the flexibility in trying to compute y? And when you look at it in detail, you find that there are a set of y's, well, at least y, but h, such that add h of y is minus y, is determined by a set of linear equations involving well, at least involving the weight in question, delta alpha, as alpha runs through pi, and the number of such linear equations of number equal to, because some of them are the same, the cardinality of pi over the orbits of W0. Now, of course, H is in the Cartan. The Cartan has the same dimension as the cardinality of pi. So if I were to be inflexible and only have this, then there would be a unique solution. However, this is not the only thing you have to worry about. There are some other conditions which are rather less easy to describe, but when you've done this part, you get an H, and then you have to look for appropriate roots. And that process is sort of not a linear process, and it may be that when you have a solution to just this, the appropriate roots are not available. But it turns out that if you allow this or this, then the appropriate roots are available. So let me now describe a solution, and it looks like a unique solution when the orbits are trivial, but I have no idea whether it's a unique solution or not. So we want to solve for y, or solve for h, which is the same thing, because h will determine y. H will be y will be the minus 1, will be formed from the as an element in general position of the minus 1 eigenspace of H. So a solution, or description of a solution. For y. For h, just for h. Okay. So the idea is to decompose pi into two subsets, pi a and pi b, where the elements of pi a or the elements of pi b are all orthogonal to one another. And there's just one way to do this, and you immediately see something which perhaps will make you understand something about these epsilons. So for example, pi a could be these four guys, and pi b could be these four guys, or the other way around. So that's a decomposition. And having done that, I then get two involutions, which are just the product of the simple reflections as alpha runs through pi a, and similarly for sigma b. And then I get from that a Coxeter group, since these things are obviously involutions, with two generators. And we have a couple of nice facts, which I don't claim to be original, but they're certainly useful. And let's consider the case where the Coxeter number is even, where, let me just point out that sigma a, sigma b is a Coxeter element, and then c will be the order of sigma. So in this case, it's a fact that every c orbit meets pi at exactly one point. So therefore, if you take the highest root, which I'll call beta star, then, and I apply C to it, this will meet a unique element, let me put it like this, which I'll call alpha star. And since, well, let me make the convention that alpha star lies in pi a, and then the stabilizer in C of alpha star will be sigma b. So now, how do I describe H? I simply take W. So let W of C be the unique element in C, such that, first of all, WC of alpha star is beta star. But since you have a stabilizer, we want some other condition, and that is that the parity of C over 2, which remember is a Coxeter number, and I'm assuming it's even, is the same as the parity of the length of WC viewed as an element in this Coxeter group C. So that explicitly describes implicitly describes WC. And all I can say for the proof is that it works. Now let me just finish with the description of V. And basically what I want to just say is that this involves some further strange coincidences. So let me give a description of C, a description of V. And really I just want to give the coincidences. So we've described Y, now what about V? Well, there's something which is called now the constant cascade, which is very fundamental in this whole business. And it's got as follows: let delta be the root system. The constant cascade is associated to a root system, and it consists of the highest root and the constant cascade of everything orthogonal, and I won't write down the definition, but everything orthogonal in the root system to B star. It's got a natural ordering on it, and so on. Now, fix H in H, and let me call it H star, and this is somehow the antithesis of this H over here. I can't really explain why, but it's sort of the antithesis of it. Let me just say that H over there is WC of the standard H, of H1, where H1 on alpha is 1 for all alpha in pi. I forgot to say that before. So this guy is somehow the antithesis of it. That's a regular element. This is a completely irregular one, such that H star of beta is 1 for all beta in the constant cascade. Let me assume that the Coxeter number is even, and let me also impose, since it's necessary in general, that kappa of H star is H star. Otherwise, it's not unique. And then the remarkable thing is, and I don't know if this has any more use, that H star of alpha is in the set -1, 0, 1 for all alpha in pi. And this is used in constructing V. And let me just end with a very surprising fact, is that H star of alpha is -1 if and only if epsilon alpha is 1/2. And there are some other conditions for H star alpha being 0 and H star alpha being 1. And this is used in constructing V. and give some perhaps new insight into the nature of this epsilon alpha. And in fact, if I compute H star alpha in type E8, then I find that the numbers are -1, 1, -1, 1, 1, -1, 1, and -1. Where those numbers are exactly the values of H on the given roots. Okay, I'll stop.
Any questions?
Yeah, in this case, E8, you have partition to disjoint. Is the same for other diagrams?
Yes, yes. You mean by virtue of the values of
Right. Yes, it's once form kind of disjoint. Second -1 also disjoint.
No, that's not true in general. Let me give you one other example. E7, of course, E7 is okay, but let me take D5. Then it's -1, 1, 1, and I think it's 0 here and 0 here. So you see, this can also have values in 0. And for example, in type A and C are special here. So A is 1, A2n plus 1, where the Coxeter number is even, is like this. This is A7, and C, whatever, is 1 here and 0 everywhere else. So lurking behind all this business, which makes me very happy, is that we have a general theorem, but when we look at the details, for example, the nature of this function, we see differences between the different types. So A and C are special because you only have values which are 1 and 0. You never have -1. So you see the differences between the different types, even though you have a general theorem.
Any other questions or comments? So let's thank the speaker now.